The gasoline engine is used in passenger cars and trucks to furnish power to drive the wheels through the transmission and driving axle. The source of this power is energy stored in the gasoline, energy that is released when the gasoline burns in the cylinders of the engine. Let's move in a little closer and look at that basic process. In a gasoline engine, round pistons are fitted closely in hollow tube-shaped spaces which are called cylinders. There is a closed-in free space on top of each piston, and periodically a mixture of gasoline and air is let into this space and compressed. Then it is ignited or set on fire and burned. As the gasoline burns, it releases gases that have a great tendency to expand. Expansion of the gases causes a very high pressure above the piston, pushing the piston down very forcibly in the cylinder. Therefore, as the piston moves, the expansion of the burned gases then becomes power. Since the piston is confined in a straight cylinder, it moves in a straight line. To harness this power to turn the wheels, it must be changed from straight line motion to rotary motion. This is accomplished by connecting the piston to a crankshaft. Now, if we can make the piston move up and down in the cylinder, the crankshaft will be forced to turn. Then, repeating the burning process above the piston will cause repeated bursts of power to keep the crankshaft turning. Now, at this point, we have shown only how to push the piston down, not how to get it back up again. That takes another part of the engine, called a flywheel. The flywheel turns with the crankshaft, and because it is very heavy, keeps the shaft moving when the piston is not being pushed by burned gases. Actually, as the engine has several cylinders, they can be timed to fire one after another, so that the motion of the crankshaft is maintained by an alternating force on all of the pistons. However, a flywheel still is used to keep the crankshaft turning smoothly. Without it, power would be applied unevenly each time a cylinder fires. The process of burning gasoline to produce power this way is called combustion, and it happens in a closely controlled cycle. The space above the piston, known as the combustion chamber, is fitted with two valves. The intake valve lets the air-fuel mixture into the cylinder before it burns, and the exhaust valve lets the burned gases out. An electric spark plug in the combustion chamber provides the spark for ignition at just the right point in the cycle. The complete combustion cycle for each piston takes 4 strokes of the piston. A stroke is the movement of the piston from its highest place in the cylinder to the lowest, or vice versa, which requires 1/2 turn of the crankshaft. The first stroke of the cycle is the intake stroke. Starting at the top of the cylinder, the piston is pulled down by the crankshaft, with the intake valve open. This movement creates a vacuum or suction condition above the piston. The air-fuel mixture is drawn into the cylinder past the open intake valve. When the piston reaches bottom and starts up again, the intake valve closes and the compression stroke begins. The exhaust valve stays closed so that the air-fuel mixture is trapped above the piston and compressed. Compressing the mixture enables it to burn more readily and release more power when it is ignited. The spark plug fires to cause ignition just before the piston reaches the top again. The third stroke, then, is the power stroke. Combustion is already well in progress as the piston starts down again, with all the pressure of the expanding gases pushing the piston to drive the crankshaft. Near the bottom of the power stroke, the exhaust valve begins to open. As the energy of the burned gases is used up, the exhaust gases must be removed from the cylinder. This final stroke in the cycle is the exhaust stroke. The piston again is pushed up in the cylinder, and the cylinder is emptied of gases through the open exhaust valve. The cycle then begins again with the intake stroke as the piston completes the exhaust stroke. The entire four-stroke cycle takes 2 revolutions of the crankshaft. That, very quickly, is how the engine operates. To make the process happen continuously and reliably, the engine must have 7 operating systems. Let's name them now, and then we'll look at them individually. The compression system includes the parts that seal the combustion chamber and transmit power and motion of the piston. The valve train is the system that opens and closes the intake and exhaust valves at the proper times in the combustion cycle. A lubrication system is used to circulate engine oil to lubricate all the moving parts of the engine so that they slip and slide instead of grinding against each other. The cooling system circulates coolant through the engine to remove the heat of combustion from the engine parts. An induction system provides the mixture of fuel and air for combustion. The ignition system attends to firing the compressed mixture from an electric spark at just the right instant. And the exhaust system disposes of the burned gases after they've done their work. There are many variations of basic engine design which also should be mentioned in this introduction, as well as some basic design characteristics you must be aware of. The cylinders may be arranged in line, that is, all in a straight row, and this is the usual arrangement for 4-cylinder and 6-cylinder engines. For 8-cylinder engines, a V arrangement is the general rule. 2 inline banks of 4 cylinders each are arranged at a 90-degree angle to each other. There are also V4 and V6 engines that use the same design characteristics. Valve trains are usually designed with overhead valves. That is, the valves are located in the top of the combustion chamber. If the camshaft that operates the valves is also located up there, the valve train is referred to as an overhead cam type. The engine cylinders come in various sizes. The bore is the diameter of the cylinder, and the stroke is the full travel of the piston from the top dead center to the bottom dead center position in one stroke. Between them, bore and stroke determine the displacement of the cylinders. Displacement is the volume of the cylinder in the distance the piston travels. It is expressed in cubic inches, cubic centimeters, or liters. The total engine displacement equals the displacement of one cylinder multiplied by the number of cylinders. In general, the higher the displacement, the more power is available from the engine. Increasing either the bore or stroke, or both, will increase displacement and power. Compression ratio is the amount the air-fuel mixture is squeezed or compressed. In this example, the volume before compression is 8 times the volume after, so that the compression ratio is 8 to 1. The compression system is the main structure of the engine. It includes the parts used to seal the combustion chamber, compress the air-fuel mixture, and receive the power generated when the mixture burns. The engine cylinders are arranged in a large iron casting called the cylinder block. Above the cylinder block is a cylinder head, which forms a roof for the combustion chambers. The pistons then are fitted into the cylinders as floors for the combustion chambers. They are linked to the crankshaft by connecting rods and bearings. The crankshaft is mounted in bearings at the bottom of the cylinders and is used to receive the engine's power on one stroke and push the pistons back and forth on the other 3 strokes. Compression is sealed in this system at 5 points: at the heads of the 2 valves, at the spark plug, at the cylinder head gasket, and at piston rings, which run against the sides of the cylinders. All of these sealing points are critical, since any loss of compression will mean a loss of power and leakage of combustion gases during the power stroke. With that identification of the system components and functions, let's look at the pieces one by one, somewhat in the order of building the engine up from loose parts. The cylinder block is the main supporting part of the engine. It is usually made of cast iron, with the cylinders machined carefully for true roundness and square alignment with the crankshaft. Other parts of the cylinder block are the engine mounts, water jackets, and lubrication passages. In fact, the block has provisions for parts of all the 7 systems of the engine, as we'll see. At the bottom, the cylinder block is flared out so that it forms the upper part of the crankcase, providing a space for the crankshaft to turn with clearance for the cranks. When the engine is assembled, the oil sump pan is bolted onto the skirt of the block to form the bottom of the crankcase. Let's turn the block over now to see how the crankshaft is mounted. This block has 7 main support surfaces for the crankshaft of a 6-cylinder inline engine, which is a pretty long crankshaft. There will be fewer supports for shorter crankshafts. The crankshaft will be mounted on insert-type main bearings on these supports and attached with main bearing caps. The term main, incidentally, refers to the parts used in mounting the crankshaft. Each of the main supports contains an oil passage. These passages will align with holes in the main bearings to lubricate the crankshaft as it turns in the bearings. The crankshaft for this engine, then, has 7 main bearing journals to mount on the main supports. A journal is a round bearing surface. The main bearing journals are all in a straight line, and they alternate with the offset journals, which are for the connecting rods. Notice that the rod journals are at various positions around the shaft, so that the pistons will be at different places in the cycle. Another common name for the connecting rod journal is crank pin. The side supports for the rod journals are called webs or throws. Counterweights may be cast into the shaft opposite the rod journals to compensate for the off-center weight. This balances the crankshaft so that it doesn't vibrate in high-speed operation. The crankshaft must be built husky to handle the tremendous forces of the engine's power strokes. It is generally cast or forged in one piece of high-strength cast iron, then machined to very close limits. All the journals are highly polished to reduce friction and are held to very close roundness so they turn true in their bearings. Oil passages are drilled in the main journals to receive oil from the main supports in the cylinder block. This oil is then routed through slanted passages in the crankshaft that lead to the connecting rod journals to lubricate the rod bearings. There also is a thrust surface on both sides of one of the main bearing journals to control the front to rear positioning of the crankshaft. The V8 crankshaft is shorter than the 6-cylinder. This one has 5 main journals, alternating with 4 connecting rod journals. Each of the rod journals will have 2 rods connected to it, one from each bank of cylinders. As the engine operates, the crankshaft must handle forces of up to 2 tons on the connecting rod journals, which does tend to twist the individual crank pin a slight bit ahead of the rest of the shaft while power is being applied. Of course, the force is relieved as soon as the power is spent, so that the crank immediately flexes back to its normal position. What happens then is a torsional or twisting vibration going on constantly in the crankshaft that must be controlled. The device used to control torsional vibration is called a vibration damper. It is mounted on the front of the crankshaft and acts as a kind of shock absorber. The crankshaft main bearings are the split sleeve type, meaning each bearing has 2 halves which together form a single sleeve for the journal. The upper half has an oil hole and goes into the bearing support. The other half goes into the bearing cap. Sometimes the bearing halves are interchangeable. The wearing surfaces of the bearings are made of a softer material than the crankshaft, so that if wear occurs, you can replace an inexpensive bearing rather than a very expensive crankshaft. Also, the soft material reduces friction, tends to mold itself to any irregularities of the shaft journal, and may even allow small metal particles to embed in the bearing so that they don't scratch anything. When the crankshaft and bearing caps are installed, there is a slight clearance between the bearing and the journal. Oil from the upper bearing hole circulates through the clearance for lubrication. Then it is thrown off into the crankcase. Circulation of the oil also cools the bearing and flushes away grit and dirt that may have worked into the bearing. So there must be enough clearance to maintain circulation. Otherwise, excessive wear will occur quickly. However, the clearance must be carefully controlled, because even small increases in clearance cause steep increases in the amount of oil that can flow through. If the clearance gets too great, the oil pump can't keep up. Oil pressure will drop in the engine. Some of the bearings may not be oiled continually, or other parts of the engine may be starved for oil. Both main and connecting rod bearings come in a selection of sizes, so they can be fitted for a close to ideal clearance when the engine is built up. This clearance allows for normal bearing wear without a loss of oil pressure. On most engines, one of the crankshaft bearings will be a thrust bearing with flanged thrust surfaces to limit the fore and aft movement or free play of the shaft. However, on some engines, individual thrust washers are installed to perform the same function. We can conclude the crankshaft story now by identifying the parts installed with the crankshaft and its bearings on the engine. At the front of the engine, the vibration damper assembly includes a V-groove pulley. This pulley turns with the crankshaft to drive the engine's fan belt and other accessory belts. The front main oil seal and rear main oil seal fit around the crankshaft to prevent leakage from the ends of the crankcase. Also at the front of the shaft is a gear or sprocket that will be used to drive the valve train camshaft in time with the crankshaft. The flywheel bolts onto a flange at the rear of the crankshaft. A starter ring gear is attached to the flywheel to crank the engine when the starter is operated. Now let's go on to describe the piston and connecting rod assembly, which would be the next installation after the crankshaft. A steel piston pin, sometimes called the wrist pin, connects the rod to the piston. This pin must be free to turn in either the piston or the rod, so that the rod can rock back and forth as the crank turns. In some engines, the pin turns freely in both the piston and rod and has retainers at both ends to keep it from sliding out. The large end of the rod is connected to the crank pin by a rod bearing cap. The rod bearings are pretty much the same type as main bearings, with equally critical clearances. The oil holes in the bearings are mated with holes or notches in the rod to squirt oil against the cylinder walls for lubrication and cooling. The piston is closely fitted to the cylinder with thrust surfaces on the piston skirt to guide it in the cylinder bore. The skirt is often narrowed to provide clearance with the crankshaft counterweights. Most pistons are made of aluminum to keep their weight moderate. Because aluminum expands greatly with heat, steel struts are usually cast into the piston to control the expansion. The top of the piston has ring grooves machined into it. Piston rings are installed in these grooves to seal against the cylinder walls. That way, the piston can operate with some clearance for lubrication and heat expansion. Most engines will use 2 compression rings and 1 oil control ring on each piston. A 3rd compression ring is added on some heavy-duty truck engines. The compression rings are solid in construction. They go into the topmost ring grooves to seal the combustion chamber from the crankcase. Also, the compression rings scrape some oil from the cylinder walls on their downward strokes. However, they have a built-in twist so that they skim over the oil film on the compression and exhaust strokes, preventing the oil from being scraped into the combustion chamber and burned. Oil control rings are needed mainly because the small clearance between the piston and cylinder won't handle all the oil the compression rings can scrape. The oil rings also do part of the scraping, and they are slotted or segmented to direct the oil to a slot in the piston behind the ring. From there, it flows into the hollow space inside the piston skirt and falls back into the crankcase. All of the piston rings have one more function, and that is to carry heat away from the piston to the cylinder walls, which are cooled by the water jacket. The last part of the compression system is the cylinder head. It also is a supporting part of the engine and is built sturdily of cast iron. In addition to forming the top of the combustion chambers, the cylinder head provides mountings for the intake and exhaust manifolds, spark plugs, engine valves, and other components of the valve train. Oil and water passages also are part of the cylinder head. The cylinder head is mounted on top of the block with a flat gasket, which seals the combustion chambers and water and oil passages from each other, and also from external leakage. It's customary to replace the head gasket each time the cylinder head is removed, since this sealing is so critical. Also, there is a particular sequence for tightening the cylinder head bolts to assure a good seal. The valve train is used to open and close the valves in the combustion chamber. The valves open and close in proper sequence so that the air-fuel mixture can enter, compression and ignition can occur, plus burned gases exhausted. Today's engine valves are mushroom-shaped, with a head to seal the valve port, blending into a stem that guides the valve. One or more grooves or slots are machined into the stem to accommodate a spring retainer. The sealing surface of the valve is a tapered face that is ground around the stem side of the head at an angle. The seat it seals against will be ground at nearly the same angle to provide a tight seal. Opposite the valve face, the head has some reserve thickness, which is called margin. This allows the valve head some extra capacity to absorb heat. It also allows some valves to be ground to a new finish and reused. The stem of the valve pilots it in a valve guide, so that the face seats squarely every time the valve closes. Both the seat and the guide are installed or machined into the cylinder head. Engine valves are made of a special high-strength steel that is especially heat resistant. Exhaust valves get the hottest. In fact, they operate red hot because of the heat blasts from the burned gases flowing past them. Heat is transferred from the valves in two ways, from the head to the seat, and from the stem to the guide. Obviously, it is desirable to move as much heat as possible to the stem, since its guide is in a cooler place and has a big surface available. So some exhaust valves have hollow stems filled with sodium, a liquid metal that conducts heat very readily. When a sodium valve is discarded, it should be buried, never cut open, because sodium burns violently in the air. The valve seat must be rather hard because it takes a constant hammering as the valve opens and closes. It also has to be able to resist corrosion because of the heat and combustion gases in the area. When the cylinder head material meets these requirements, the valve seat can be cut into the head. If not, it will be a hardened steel insert that is pressed into the head. The valve seat has three machined surfaces: the seat plus an upper and lower clearance. The clearances are cut to make the seat narrow and to center it properly against the valve face. This provides a better seal and prevents the carbon deposits that could collect if the seat was too wide. Valve guides are usually machined into the cylinder head. In some cases, though, cast bushings are pressed into the head. There is a very close fit between the valve stem and the guide, with just enough clearance to allow lubrication and a slight bit of heat expansion. The cold clearance may be higher for the exhaust valve since it gets hotter in operation. Now, let's look at the parts that cause the valves to open and close. And we'll start with the overhead valve, or OHV train, which is most widely used today. The engine camshaft is located in the cylinder block and is driven from the crankshaft. It has a number of cams, which are partly round, but have lobes, or noses, that extend beyond the base circle. As the camshaft turns, the cam moves against the valve lifter, which also may be called a tappet or cam follower. The lifter is raised whenever the lobe of the cam is up and allowed to come back down as the lobe moves past it. Above the lifter is a push rod, which moves up and down with the lifter and transmits the cam action to the rocker arm. The rocker arm is a pivot lever that actually opens the valve. As the push rod tips the end of the rocker arm, the opposite end pushes against the stem of the valve to push the valve off its seat. To get the valve closed when the cam lobe moves past the lifter, a spring is installed between the end of the valve stem and the cylinder head. The valve spring is compressed as the valve opens. Its force then pushes the valve closed again, and also pushes back through the valve train so that the lifter is forced to follow the surface of the cam. For proper timing, the camshaft is driven at exactly 1/2 of crankshaft speed, since it takes 2 revolutions of the crank to complete 1 cycle of combustion. On some engines, the drive is direct. A small gear on the crankshaft drives a larger gear on the camshaft. Other engines use a chain drive with sprockets on the camshaft and crankshaft. In both types, the camshaft gear or sprocket has twice as many teeth to reduce its speed to 1/2 crankshaft speed. The overhead cam, or OHC valve train, has the camshaft installed on the cylinder head above the valves and eliminates the need for lifters and push rods. In this arrangement, the rocker arm is the cam follower, and the valve opens as the cam lobe bears against a machined surface on the arm. Valve springs are used the same way as on OHV systems. The overhead cam is driven by sprockets and a chain or notched belt. A tensioner assembly is installed against the belt or chain to prevent slipping, which would upset the valve timing. That is the story on how the overhead valve and overhead cam valve trains operate. Now let's take a brief look at the components. The camshaft is made from a very hard cast alloy material so that the cams can be very wear resistant. This is a 6-cylinder camshaft and has 12 cams arranged to time the opening and closing of the intake and exhaust valves. It also has a spiral gear, which will drive the engine oil pump and distributor, plus an eccentric, which will drive the fuel pump. The camshaft is installed in the cylinder block in sleeve-type bearings, which have holes connecting the bearing journals to a lubricating oil gallery in the block. There is a thrust surface on the front of the camshaft, which controls the fore and aft movement through a thrust plate and a spacer on some engines. The valve lifter originally was a solid piece of steel designed to follow the cam and transmit its movement to the valve. This solid type of lifter still is used on some engines. With solid lifters, it is necessary to set a small amount of clearance in the valve train. This clearance assures that the valve has room to close fully, but may also allow some noise to develop as wear occurs. Adjustments of valve clearance are part of periodic maintenance. Most U.S.-built engines today are using hydraulic lifters, which take up the clearance automatically and keep the valve train tight without preventing the valve from seating fully. The hydraulic lifter has an inner plunger that operates inside a lifter body. The lifter body follows the cam. The plunger is spring-loaded and has a cup at the top which bears against the push rod. A check valve at the bottom leads to an oil chamber between the body and plunger. When the lifter is on the low part of the cam, the engine valve closes. If there is clearance in the valve train, the spring will push the plunger to take it up. At the same time, pressurized engine oil flows through the body and plunger and past the check valve to fill the chamber under the plunger as the plunger moves upward. Then, as the cam lobe comes up, the check valve is closed by spring pressure to seal the oil under the plunger. The oil is not compressible, so the lifter, in effect, is solid and will move the valve train with camshaft rotation. There is a very small amount of oil leakage past the plunger to prevent the lifter from pumping up. It is critical that the plunger leak down isn't excessive, or the valve won't open enough. Conversely, not enough leak down will hold the valve open. Hydraulic lifters usually are tested for leak down before installation in the engine. Push rods are made of stiff steel tubing with cups or balls on the ends to operate against the lifters and rocker arms. There is some flexing of the push rod in operation, and this is allowed for in designing the amount of valve opening. There are two types of rocker arms. The shaft-pivoted rocker arms are made of cast iron and mount on a hollow rocker arm shaft, which supplies lubricating oil to the arm's oil holes. Stud-pivoted or pedestal-type rocker arms are made of cast iron or stamped steel. They are mounted on ball sockets atop steel studs. The lock nut that holds the rocker arm on the stud provides the valve clearance adjustment on some engines. Turning the nut up or down raises or lowers the arm to increase or decrease the clearance. Valve springs are very stiff so that they close the valves positively. They are checked closely for squareness and have the ends machined flat to prevent any tendency to cock the valve. The spring is installed over the valve stem with a retainer that is secured by split locks installed in the groove in the valve stem. A cup-type oil seal under the spring prevents oil from the spring, retainer, and valve stem from being drawn through the valve guide into the combustion chamber. The valve spring tension is critical because a weak spring can let the valve stay open at high speed, but too much force speeds up cam wear. So valve springs are checked for proper tension before they are installed. Another critical factor is the spring working height, which changes if the valve or its seat is refinished. Shims are available to adjust the installed working height so that the spring will exert its full closing force on the valve. There are still 5 systems of the engine to describe. However, this final part will deal most importantly with the lubrication and cooling systems, and in less detail with the systems that have their own training courses. The lubrication system delivers a steady supply of engine oil, providing a slippery film for the moving parts to run on. Because the oil is constantly flowing, it is able to help cool the engine and clean some parts of it as well as lubricate. The main parts of the lubrication system are the sump pan, where the oil is stored, the pump, which circulates the oil through the engine, a filter to keep the oil clean, and of course the oil passages in the engine cylinder block, head, and other parts. Operating at a pressure of about 50 psi, the system pumps oil first to the main oil gallery, which feeds the crankshaft and camshaft. Thus, full pressure lubrication is used for the camshaft journals, the hydraulic lifters, main bearings, and rod bearings. Beyond the main gallery, pressure is reduced by restricting the size of the passages. The valve train parts, other than the lifters, generally receive a lower pressure oil feed. And as the oil drips back to the oil pan, it lubricates the parts that are not pressure fed or lubricated by oil mist from the crankcase. Engine oil pumps are the positive delivery type, which means that they pump more oil as the engine speeds up. The pump output is in proportion to engine speed and is usually more than the system needs. So the pump is equipped with a pressure relief valve. When a preset pressure is reached, the relief valve returns any excess pump output to the oil pan or the pump inlet. Ford oil pumps are the rotor type, using 2 rotors with meshed lobes to form a pumping mechanism. The inner rotor is driven from the camshaft, and its lobes drive the outer rotor. An oil pickup is part of the pump assembly and provides a path from the oil pan to the pump inlet. It is submerged in the oil and contains a screen or some sort of coarse strainer to keep large particles out of the pump. The oil filter provides a very fine trap to remove small particles from the oil that may pass through the pickup screen. It is installed in the pressure line from the pump. All the pump output goes through the filter, so we call it a full flow filter. Oil from the pump enters the filter can through a number of holes and flows around the outer part of the element. It then flows through the element into the center and to a tube leading to the main oil gallery. A bypass valve is part of the filter assembly. If the element becomes clogged, this valve will open to let oil circulate so that the engine won't be destroyed due to oil starvation. Now let's turn our attention to the cooling system, which is designed to circulate a mixture of water and antifreeze through the engine to carry away the heat generated by combustion. The main components of the cooling system are a pump to circulate the coolant liquid, water jackets in the engine that carry the coolant around the cylinders, and a radiator which transfers the heat in the coolant to the outside air. Hoses connect the radiator to the engine and to the water pump. Most cooling systems will also have a fan to pull air through the radiator, a pressure cap to help raise the maximum operating temperature of the system, and a thermostat to speed the warm-up of a cold engine and control the operating temperature. Also, some sort of temperature indicator is used to warn the driver if the system overheats. Here is a typical example of how the coolant circulates in the engine. As the engine operates, coolant in the water jackets in the cylinder head and block warms up until it is warm enough to cause the thermostat to open. Then, pressure from the pump pushes the coolant out of the cylinder head jacket, through the thermostat and upper hose, and into the radiator upper tank. From there, it flows through tubes in the radiator to the lower tank. The fan pulls air through the radiator fins to remove heat from the coolant as it is flowing from tank to tank. From the bottom tank, then, the flow path is through the lower hose to the water pump inlet, through the pump, and into the cylinder block water jacket, which also connects through the head gasket to the cylinder head water jacket. There is also a small diameter bypass passage between the engine and pump. Its purpose is to let the pump circulate the coolant through the water jackets while the thermostat is closed, providing a more even and rapid warm-up. The water pump operates by centrifugal action. An impeller with vanes turns inside the housing, and the vanes sling the coolant from the center of the impeller to the outside of the housing and to the pump outlet. The water pump shaft supports the engine fan and pulley as well as the impeller and is mounted on a double row bearing. Both the fan and pump are driven by the fan belt from the engine crankshaft. Pressure caps are used on most modern cooling systems because increasing the operating pressure raises the boiling point of the coolant. This lets the engine run hotter and the cooling system work more efficiently. A typical pressure cap has two safety valves: a blow-off valve to let off steam when the pressure gets too high in the system, and a vacuum valve to let outside air in if a vacuum is created when the engine cools down. The thermostat is nothing more than a valve that is controlled by heat. As the engine warms, a wax-filled pellet expands to open the passage and allow coolant to circulate to the radiator. The coolant most often used today is a mixture of water and glycol, more commonly known as permanent antifreeze. Alcohol also is used for antifreeze, but boils at low temperature and therefore is unsuitable for pressurized systems. The fuel induction system is the supplier of air and fuel mixture to the cylinders. By fuel, of course, we refer to gasoline. The gasoline is first stored in the vehicle's fuel tank, which is installed some distance from the engine. A fuel pump moves it through fuel lines and a filter to the carburetor. The carburetor is a device that partially vaporizes the fuel and mixes it with air. An air cleaner on top of the carburetor filters the air so that the mixture will be clean. From the carburetor, the mixture flows into the intake manifold, a system of ducts that distributes the fuel to the intake valve ports. From there, the valve train takes over to get the fuel into the cylinders. A fuel evaporative emission control system operates within the fuel system. As the name implies, it controls the loss of raw fuel vapors to the atmosphere. Essentially, it is a sealed system which traps fuel vapors and directs them to the engine so that they are burned in the normal combustion process. After the fuel burns, the exhaust system collects the combustion gases and discharges them into the atmosphere at some safe place away from the passenger compartment. Of course, these exhaust emissions are controlled so that they are within the standards allowed by government regulations. Collection of the gases starts in the exhaust manifold or header, which is bolted onto the cylinder head and mates with the exhaust valve ports. From the manifold, the gases flow through an exhaust pipe, then through a muffler to deaden the engine sound, and finally through a tailpipe to the outside air. A second muffler, or resonator, may be used on engines that need more sound deadening capacity. Finally, the ignition system provides the timed spark to the cylinders to set the compressed air fuel mixture on fire. Electricity for the spark originates in the battery. The ignition switch turns the system on when the driver turns the ignition key in the lock. A coil transforms or steps up the battery electricity to a very high voltage so the spark will be powerful. The distributor receives this high voltage and passes it on in turn to the spark plugs, which fire to ignite the fuel. And there you are. The modern gasoline engine is a marvel of engineering and the workhorse of most automotive transportation. Knowing how it works is your first big step in learning how to keep it working well.